Hello everybody. Indeed, my name is Aurélien Crida. I'm a professor at the Université Côte d'Azur in Nice, in the southeast. And I will tell you about solar system formation, mainly the basics of planetary formation in this first half of the lecture, so 1 hour and a half. And after the break, we will go on generalizing planet formation to exoplanets, see some specific features of the dynamics of the solar system, and then I will go a bit deeper into some thoughts that all this should bring to us. But let's start with really the basics. On this image, you can see stars in the sky, and maybe some of you can recognize some figures, some done by the stars here, some typically these 3 stars aligned here. Do they ring a bell to somebody? Orion, right. And you have here also a V shape, which is very typical. That's Taurus. And here is Auriga, this nice pentagon. So you recognize these constellations, which comes from the Latin cum stelle, made with stars, because the stars don't move with respect to one another, basically. Of course, on million years scale they do, but on mankind's time scale they don't. And so these are very well remarked feature that most civilizations have identified and that don't move within centuries. You also notice on this picture the top of the VLT at the Cerro Paranal in Chile, because this is where the picture was taken. You will have recognized that Orion is seen upside down with the nebula here instead of being on the other side, because we are here in the southern hemisphere. But the other thing you can notice is this bright spot here, which does not belong to one of the constellations because it's not always here. This thing is actually Venus and is moving around like some dots in the sky who do not belong to constellations and keep moving with respect to the other stars. There are 7 anomalies like that that can move in the sky with respect to the fixed stars. Do you know which are these 7 anomalies? You probably heard them because they are the 7 days of the week. There's the moon, Monday. There's Mars, Tuesday. Okay, with Mars and Tuesday the connection is not obvious, but there is a connection. Mars is the god of war, and the god of war in the Nordic and Germanic pantheon is some guy whose name looks like Hughes, and I don't remember. Probably some of you know. Wednesday for Mercury is exactly the same. Thursday for Jupiter is more clear. It's Thor, the god of thunder. In German also, Thursday is Donnerstag, clearly the day of thunder, because Jupiter is the god of thunder. Venus, Frey was the goddess of love in the Nordic pantheon, so Friday. Saturday and Sunday are clearly obvious. These are the 7 things that you can see with the naked eye move with respect to the other stars. And that's the only ones. And these things that move are called in Greek planetes, and it has given the name planets. So initially you see that the planets were not what you know now as planets, but just things that move in the sky. Then, where do they move? Not everywhere. And that's the whole point of Tintin and the Mysterious Star, where he wanders in Brussels, sees the night sky, and recognizes here the Big Dipper, the Big Bear. And surprise, there's a new star in the middle. And that's the beginning of a great adventure. But that's because it has never been seen. But a star in the middle of between Taurus and Auriga, that's something that is often seen. Planets wander here. Actually, planets do only wander in a region of the sky which is called the zodiac, and that's shown on this map of the sky in May 2007. You have Mercury, Venus going from here to there during the whole month. Saturn is here, and further than another one. And the fact that they all move in this band in the sky, in this region, just tells us that the solar system is flat. It's the same reason why if everybody moves in this room, we will only see heads in front of the walls, and we will never see a head in front of the ceiling or the ground, because we all move in the same plane. So the fact that the planets move in this plane, which is called the ecliptic plane, tells us that the solar system is flat. And this is an obvious observation that you can make with the naked eye, and you start have a feeling of what our world is, how the world is around us. It's all flat. And that's something that you can even see better on this image, where you have here, I think, 5 planets aligned. You can't see the text, but it's Saturn on the top, Mars, Venus, below is Regulus, so that's a star, doesn't count, and there is Mercury. You can guess that the Sun has sat just behind the horizon, and you can see, of course, a last planet, the Earth. All aligned. This picture shows the zodiacal light. It has been taken at Maui Observatory in Hawaii, where the night sky is particularly black. And it's something that is hard to see, but you can see if you have a nice dark night. Just close after the sunset, you would see this kind of column of actually dust illuminated by the sun. This is all the dust produced by comets, collisions among asteroids, and whatever processes that tend to produce dust in the solar system. They tend to happen in the ecliptic plane. So the sun is actually surrounded by a disk of debris, very tiny dust, which is hard to see. It's not dense at all. But of course, the sun is enlightening this, and you can see this under good conditions, and it marks the plane of the solar system, the ecliptic plane. So with everything in this plane, I think it's important to remember that it's not exactly in the plane. Otherwise, every time the moon passes in front of the sun or behind the Earth, we will have an eclipse. So some basic geometry here, which is important, has nothing to do with planet formation, but it's important to remember. The moon orbit has an inclination of 5 degrees with respect to the ecliptic plane. As you can see on this sketch, the ecliptic plane is here in blue. I'm sorry for the caption to be in French. The moon eclipse is shown here in gray, and it has this 5 degrees inclination. And this inclination keeps constant. It's the same orientation of the plane all around the Earth's orbit. So when we are here on the left, the moon at new moon is below the ecliptic plane. And so we don't see the moon passing in front of the sun at all. There's nothing particular to see. And when the moon is on the other side, at full moon, then the moon is above the ecliptic plane and above the shadow of the Earth. So there's nothing special happening. And that's the case most of the time. But twice a year, when we are here or at the symmetric position at the bottom, the line of nodes, which is the line of intersection between the moon the moon orbit plane and the ecliptic plane, this line crosses the sun, and thus when the moon passes in front of the sun at a new moon, it's right on the axis, and when it's on the other side, it's right on the axis as well. And so you have a sun eclipse and the moon eclipse 2 weeks apart. Of course, the sun eclipse may be only partial, because if the exact moment of the new moon does not happen right when the line of node is in the sun, you can miss it a little bit, so the sun eclipses are not ideal. But the moon eclipse comes generally every 6 months on Earth. But to be able to see it, you need to be on the good side of the planet. So, of course, we don't see a moon eclipse that easily. But they happen. Okay? This notion of line of node and the frequency of the eclipse is important. And if you look at the calendar of moon eclipses, you will see that it's not always at the same season that they happen, because the plane is actually not exactly keeping its exact orientation. It has a movement of precession. So it's slightly tilting. And so the season of eclipses slightly shifts every year. Okay, that was a basic definition in the solar system based on a naked eye. At some point, we started observing the sky with refractors and telescopes. And in 1981, William Herschel, with the help of his sister, who has been forgotten in history, unfortunately, played with his big telescope in his garden and found a strange object far away, apparently moving slower than Saturn. He had just discovered Uranus. Uranus is a giant planet in the ecliptic plane, orbiting the Sun in the same direction as all the other ones. Very classic, so a new planet. Then, in 1801, Ceres was discovered. This one is between Mars and Jupiter. And people thought, that's the missing planet between Mars and Jupiter because there's a wide gap between Mars and Jupiter, and so it was strange that there is nothing here. But then, just the year after, another body was discovered in the same region between Mars and Jupiter. The year after, another one, and another one, and another one. And so it was very soon clear that it's not one planet here, but a belt of plenty of small objects. So we have called these small objects asteroids, like things that look like asters. And these asteroids are making an asteroid belt between Mars and Jupiter. It's called the main asteroid belt of the solar system. Later then, in 1846, the discovery of Neptune happened. And that's a beautiful story because the discovery of Neptune was made by calculus, by analysis. It was not by searching for the sky randomly, but following the motion of Uranus for 50 years, people had noticed that Uranus was not exactly following a good circle around the Sun, not following Kepler's law perfectly, and its motion was slightly perturbed, not a natural orbit. You can take into account the gravity of Saturn and the gravity of Jupiter that are pulling Uranus and changing its motion, and it still doesn't fit with the observations. So the idea came that maybe there was something else that was exerting a force on Uranus, and this something may be another planet behind Uranus. And by doing the calculation, it's really an inverse problem. Le Verrier, in the Observatory of Paris, with the help also of many people who did the calculations for him, mostly women, by the way, found where Neptune could be in the sky, and he decided to look at this position, but he could not do it in Paris because in Paris Observatory the telescope was not powerful enough and the weather was crappy. So he had to write to his German colleague Johannes Galle, who in Berlin looked in the direction of the sky that Le Verrier had said and found Neptune within 1 degree of the prediction. So that's a real triumph for celestial mechanics and science. You can find a planet just on paper. It was, however, not so much a triumph for France because we could not see the planet ourselves. We had to write to a German guy. And a few years later, in 1870, when Germany beat France, it was seen as a humiliation that we could not see it. So we decided to build a beautiful observatory, the best in the world, and it's the Observatory of Nice, where I'm working now. No connection between me and that, but... in 1930, a 9th planet was discovered, Pluto, beyond the orbit of Neptune, this time by chance, by looking in a telescope. But later, a long time later actually, 60 years later, other objects were found beyond Neptune, with trans-Neptunian objects. And some of them are even larger than Pluto, because Pluto was thought to be big in the first place, but then we realized that it's smaller, it has a satellite, it's bright, so it's actually a small object. And so in the 90s, at some point we had to decide, is Pluto a planet, but then also Eris, Haumea, and we have dozens of planets in the solar system? Or are we actually seeing a new asteroid belt, which is not the main asteroid belt between Mars and Jupiter, but an external asteroid belt beyond the orbit of Neptune? And we needed a clear definition of a planet, and it was officially given by the International Astronomical Union in 2006. A planet is a celestial body that orbits around the Sun, first criterion. So not the Sun, not the Moon. Okay, with respect to the 7 planetes, the old planets I told you at first, now the Moon and the Sun cannot be planets because they do not orbit around the Sun. A planet should also be a large enough body so that it has a spherical shape. If you think of, well, anything in this room, like this, it's not gravity that gives this laser pointer its shape. It's internal strength of the solid body. Okay? If I break it in two, gravity is not going to reform that. But if you try to change the shape of the Earth by putting stones on top of one another, at some point gravity will flatten this down and the Earth is going to reach its spherical shape. So if you are big enough, you have a spherical shape. And to be a planet, you also need to dominate the local dynamics. That is, that around your orbit, you're the big boss, 100 times more massive than anything else. With these three criteria, there are 8 planets in the solar system: Mercury, Venus, the Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And if you do not dominate the local dynamics, so if you fill the first 2 criteria but not the third one, then you are called a dwarf planet. A dwarf planet is not a planet that is small. It's something different. It should be one single word somehow. And it's something that corresponds to these 2 criteria. Pluto is one of them, but also Ceres and Eris in the Kuiper belt. And you can imagine some others may be discovered later. Some other basic definitions, which are probably not necessary for most of you, but experience has taught me that it's always good to remind these definitions to everybody. We call the solar system the sun and all the bodies that are gravitationally bound to it. Okay, so this includes the planets and their satellites. They belong to the solar system. Asteroids, comets, and the dust I have shown you. All this is within the gravity of the sun and orbiting around the sun. It belongs to the solar system. Typically, the size of the solar system is 1 light year. So the distance it takes light to travel in 1 year. That is 10 to the 16 meters roughly. If you go further than that, then the gravity of other stars of the galaxy is going to be as strong as that of the sun, and you may wander anywhere in the interstellar space. Closer than 1 light year to the sun, you will rotate around the sun, basically. I told you about stars. Yes, a star is a celestial body that is massive enough to make nuclear fusion and produce its own visible light. The planets, you have a definition from the previous slide, do not produce light themselves. They reflect the visible light from the sun or the star they are around. But stars produce their own light, and that's how we see them. The sun is just one star among others. The Milky Way, also called the galaxy with a capital G, which is the same thing, by the way. Milky Way, translated in Greek, makes galaxy. It's all the stars we see in the sky, all this set of stars, including, of course, our sun, but also including this concentration of stars that we can see as a white band in the sky. And exactly like for the solar system, you had the ecliptic plane where all the planets wander. If you consider the galaxy, you have this Milky Way, this band which is white in the sky, where you have a concentration of stars, which means the Milky Way, the galaxy, is kind of flattish. It has the shape of a lens, if you like, a thick disk, and we are inside it. So when we look in the direction or in the plane of the Milky Way, all we see is a lot of stars and the sky looks white. And when we look perpendicularly to it, all we see is a few stars, which is the classical night sky we have. And we only realized, the size of the Milky Way, the galaxy, is about 100,000 light years to compare with the solar system. About 100 years ago, almost exactly, it was realized that the Milky Way, the galaxy, is not the only galaxy. Think of that. 100 years ago, people thought that all the universe was the Milky Way, that it was the same thing, that there was stars around us, and that these stars formed this thick disk-shaped galaxy, and that was it. And then they realized that some clouds you see in the sky, some nebular objects, are actually other galaxies just like ours, super far away, million light years away, or billions of light years away. And it changed completely the picture, and now galaxy was not the proper name of the Milky Way, but a common name for such a universe island floating around. And now you have a galaxy with a lowercase g. That's a group of billions of stars floating somewhere in the universe. Okay? The universe being everything we can see with an instrument, and it has a size which is defined by its age. It's 14 billion light years. All right. So all this is basic astronomy, but always worth saying. Now let's get back to the topic of the formation of the solar system. If we move back to the solar system, we have realized that the planets turn around the sun in the same direction and in the same plane. And so if you wonder how the solar system formed, you can try to play the movie backwards and imagine what would happen if you would destroy the planets. If you pulverize the planets and make them tiny debris, you will end up with a disk of gas and debris rotating around the sun. And that's how independently the philosopher Kant and the scientist Laplace had first this idea that there may have been some nebular structure of a disk shape around the sun in the first place, from which the planets were born. And that's also what theory tells us, that when a star forms by the gravitational collapse of a molecular cloud of interstellar gas, at the center the pressure and the temperature will increase so that nuclear fusion begins and the star lights on. But due to angular momentum conservation, everything cannot collapse. You have a complex process that leads to the formation of a disk that you can see in theory and that you have certainly heard a lot about yesterday in Manuel Gödel's lecture. And you can also see this in numerical simulations of collapse in which you end up like here with a star and something that is rotating around it. So that's quite intuitive to admit this idea that stars form with disks around them. But it's not just intuition, it has also been observed. This is the spectral energy distribution of the young star GM Auriga. So in the Auriga constellation we have seen on the first slide. I think that you have already seen such a picture. So can you tell me what's going on here? You have the flux, the intensity of the luminosity of the star as a function of the wavelength here in micrometers. And as you can see, it has a strange shape. What's happening here? Yes?
At the last, this is the radiation of the black body of the star, and the right, the disk of the star.
Sounds good? Everybody agrees? Yes. Yes. This dotted curve is typical of a black body emission, which is given by this theoretical law. You see that it depends on the temperature, etc. But you can clearly fit this data with the black body emission of something of the order of 3000 kelvins. And then, with respect to this black body emission, there is an excess of infrared emitted here. If it were just a black body, the emission should drop at large wavelengths. This infrared excess must be some colder thing that is emitting as a black body in the infrared. And it's not one black body here. It's one black body emitting at 30 microns, one at 100, one at 300, one at 1000. So there are a lot of temperatures involved here. So it would be something that is near the star, but that is not hiding the star because we can see the star, and that has a broad range of temperatures. The best description you can have of that would be a disk around the star. So just with the spectral energy distribution of stars, of young stars, you have the idea that there are disks. And then it's always nice to have a confirmation with observations. These are pictures taken by the Hubble Space Telescope in the Orion Nebula. So the Orion Nebula is this region where you have a huge cloud inside which stars form. So the cloud is lit by these stars, which are bright. So you see the cloud, like a white cloud. And if you look carefully inside this cloud, which you can see here in the background, that's the background color, it's a gas. But in front of it, there are all these objects which are exactly a young star surrounded by something that is probably circular, seen slightly tilted, and looks like an opaque disk around a young star. So this confirms our interpretation of the spectral energy distribution. It's very consistent with these disks around young stars. Another observation that is very important is that if you look at clusters of young stars, typically like the Orion Nebula for instance, you can check all the stars in this cluster and count how many have an infrared excess. If they all have an infrared excess, you would be here at 100% at the top of the graph, and you can plot the percentage, the fraction of stars which have an infrared excess as a function of the age of the cluster, which can be estimated thanks to dynamics. Clusters tend to evaporate, so the larger and the less bound they are, the older they are. And you can see there are error bars in both directions, of course, but there is a clear tendency that the fraction of stars with infrared excess drops with age. And apparently, after 5-6 million years, no more star has an infrared excess. So either a few million years ago, the physics was different, and when stars formed, they did not have a protoplanetary disk, or physics has always been the same, and it just means that disks have a lifetime of the order of a few million years, and then they disappear, they vanish. Very clearly, the gas which is in orbit around the star is somehow accreted by the star or evaporated. It goes both ways, but it has to have some angular momentum transfer to leave its orbit. Basically, the angular momentum is transferred from inside out, and the gas slowly collapses onto the star. So the typical model for that is viscosity, and I think you heard about this yesterday, right? That the molecular viscosity of the gas would not be enough to create all this friction. So it has long been thought that the gas was turbulent, and that turbulence was mixing gas parcels that orbit fast with the gas parcels that orbit slow, so that it would transfer angular momentum and eventually make the cloud collapse. But the new results suggest that turbulence may not be so efficient actually. And a new vision of protoplanetary disks has emerged in which it would be more the action of the magnetic fields, either the one of the star or fossil magnetic field from the surrounding environment, that would be trapped by ions in the gas and then have an effect of slowing down the rotation of the gas, which eventually can produce winds and superficial layers that are accreting fast onto the star. It's very complex. I will not go into details about this, but there are processes that can explain that in a few million years, the gas loses angular momentum and the disk is gone. Which means we have just a few million years to form planets. Remember that. Another beautiful observation is this one made by ALMA, which is the Atacama Large Millimeter Array. So it's not quite a telescope as you would imagine. It's a set of 64 antennas that are good at catching millimeter wavelength. So it's infrared, if you like. And at millimeter wavelength, all we see is not the gas, but the dust aggregates, which have a millimeter in size, roughly, and they emit millimeter wavelength. And that's what they saw in this in the disk. So it's, if you like, it's probably not a good image, but kind of making an X-ray of the protoplanetary disks that were observed by Hubble. Here, all you can see is visible light blocked by very thin dust. And if you want to see what's inside these things, you look at millimeter wavelength and you see big clumps of dust which do not have the same distribution at all. It's much flatter than the disks we saw before. You can clearly see that there is a ring without dust here, and this ring can be seen all along. So if it were thick, here we would not be able to see the ring because of the thickness of the other rings. So it's flat and it has rings. There are regions with other concentration of dust and regions devoid of dust. How to explain this? It was kind of unexpected. When this image came, all the community, the scientific community working on this was super excited. It was the first thing. when I did my PhD, this was a dream to have something like that. And we got it 10 years later, so it's pretty cool. And things are now have even moved on. We have more images like that and more structures are seen in this. I will come back to this later. So what's the structure of a protoplanetary disk? This is a sketch where you see the disk edge-on in polar coordinates. So the vertical z coordinate is here. The horizontal line is the r coordinate, the distance to the star. And we place ourselves in a frame which is co-rotating with the gas. Okay? So we are in a rotating frame, and in this frame, the gas parcel that is here is just steady, not moving. Because it's not moving, it means that the sum of the forces it feels is 0. What are all the forces applied to a gas parcel in orbit around the star in a rotating frame? The answer is on the board. You have 3 forces that apply. The most obvious is clearly the gravity of the gas, of the star, the gravity of the star, directed towards the star. Another one which you should not forget in a rotating frame is a fictitious force. Okay, it's not a real force, it's due to the rotating frame, but it has to be taken into account. It's called the centrifugal force. Of course, you know it. It's directed in the radial direction, outwards, and its value is proportional to the radius where you are and the angular velocity squared. And one other force that we should not forget, because we are talking about a gas, is pressure. There is a pressure gradient, therefore there is a pressure force. As long as there's pressure, there's a pressure force. The expression of the pressure force is 1 over rho, the density, grad p, the pressure. The opposite of grad p, minus 1 over rho grad p. Again, I think you have already seen this yesterday, so you probably know what to do with these 3 forces. Let's analyze it first on the horizontal plane. If we project all this in the radial direction, we can say that the disk is thin, so z is negligible with respect to r, so the distance to the star is basically the radius, and the angle is basically 0, so the projection horizontally for the red arrow is minus gm over r squared. Then the gradient of the pressure horizontally is just dp over dr, and we have the centrifugal force, which leads to this equation, omega squared is gm over r cubed plus the pressure force. So if we neglect the pressure force, we recover Kepler's law. Omega proportional to square root equal to square root of jm over r cubed. That's omega k, the Kepler angular velocity, the one that all the planets follow. You know that this corresponds to having the cube of the radius of the orbit proportional to the square of the orbital period, which is a law that is well followed in the solar system. You can check that Jupiter, for instance, is 5.2 times further from the Sun than the Earth. 5.2 cube is of the order of 130, 140, and you take the square root of that and you find something a little bit less than 12, and indeed Jupiter makes an orbit around the Sun in a bit less than 12 years. Okay, so you have this proportionality. The further you are, the slower you rotate. The angular velocity is proportional to the orbital radius to the power minus 3/2. It's very important to keep in mind this Kepler's law, because it means that in a disk, the regions close to the star rotate super fast, the regions further rotate slower, and the regions even further rotate even further. So the disk is constantly sheared. There's always this motion of shear everywhere. Now, if we keep talking of pressure, this term in blue exists because clearly closer to the star, the gas is denser and the temperature is higher, so the pressure is much higher. So as you move away from the star, pressure decreases, so you have a pressure gradient in that direction, which pushes the gas outwards. And so this term, in general, is negative, so that the gas is orbiting at a slightly slower velocity than what Kepler's law would give. And it's typically noted as omega, the angular velocity of the gas, is omega Kepler times 1 minus eta, where eta is a small coefficient, which you can derive. The calculations are quite easy. It depends on the temperature and density gradient, clearly. And it makes the gas slightly sub-Keplerian. So for the gas, if you like, it's as if the star was a bit less massive, because there's not only the gravity of the star pulling towards the star, but there's also the pressure gradient that is helping to balance it. It may be a detail, but you will see later that it's important to remember that the gas is slightly sub-Keplerian because of the pressure. Now, vertically, if we project on the z-axis, the green arrow for centrifugal force disappears. We have the sign of beta, which is of the order of z over r, and you have already seen yesterday that you get a differential equation in the density, because there is an equation of state connecting the pressure with the density. So the expression 1 over rho dp over dz becomes something in 1 over rho d rho over dz. You make a separation of variables, all the rho's on one side, all the z on the other side. You integrate, and you get rho of z is actually something with a Gaussian shape. Rho 0 exponential of minus z squared over 2h squared, where h is a length equal to the sound speed divided by the Keplerian angular velocity and the coefficient square root of gamma, which we call the scale height of the disk. This is just calculation. We can go deep into it if you like, but it's not particularly interesting. But you see, it's easy. It's all here, actually. But it shows that the disk is denser in the midplane at z equals 0, and its density decreases as you move up, following a Gaussian shape. Okay? So you can clearly imagine the density doing so. And the typical scale height is almost proportional to the distance. So the aspect ratio, which is the ratio between the scale height and the distance to the star, is of the order of 5% in general. And as you have seen yesterday, small h is actually slightly increasing with r. So you can see that the disk is flared and is not exactly having a triangular shape on both sides, as it would if capital H was directly proportional to r, but it's slightly curved like that. This is a protoplanetary disk that is seen absolutely edge-on. We are lucky with this one, and we can clearly see its thickness as the dark region here where the light of the star cannot go through. And on top here there is some ejection phenomenon with the magnetic field of the star in green, but we won't go far into this. So now that we know how the disks are, we can start making planets in it. Finally. I'm sure you were waiting for that. That's all here. So if you remember that, we can finish the lecture here. Note this slide. The 6 steps, of course it's schematic, but that's the thing you need to remember if you want to have a global idea of planet formation. First thing, solids condensate into the gas. It starts very hot, and very with a low density, so it's all in terms of molecules, and at some point you make solids. Then all these solids are going to sediment to settle towards the midplane and separate from the gas, as illustrated here. That's the second step. The third step is once all these solids have reached the midplane, they aggregate into centimeter-sized aggregates of dust, which are the ones we can see with ALMA. Then these bodies these dust aggregates form planetesimals, which are of the size of many kilometers, tens of kilometers typically, which then transform by growing and merging into protoplanets and cores of size hundreds to thousands or even maybe more in kilometers. And then, as we have seen earlier, the gas dissipates in a few million years and you are left with planets. And very schematically, step number n lasts about 10 to the n years. very schematically, okay? But condensation is super quick, sedimentation is of the order of centuries, aggregation may take 1,000 years, etc., etc. It's very schematic. And of course, the time scales depend on where you are in the disk. But at a few astronomical units, that's typically what we have. And now we're going to review all these processes in 3 hours? A bit less. Okay. So of course it's going to be a short lecture on planet formation, but I want you to understand very well the structure of protoplanetary disks in which they form, because it's the framework of planet formation, and it's also an important research field at the moment, protoplanetary disks. And then if you have this in mind, you are good. But to go in detail, in terms of condensation, there's an important notion as well, which is called the ice line. The temperature in the protoplanetary disk is inversely proportional to the distance to the Sun. Temperature is in 1 over r. Maybe not quite 1 over r, but grossly speaking, that's the idea. Close to the Sun, it's hot. And so if you consider one of the most abundant molecules in the universe, and therefore in protoplanetary disks, H2O, when the temperature is above a certain value, H2O is in gas form, as we know very well, water vapor. And if you are further away, where the temperature is cold enough, H2O can become solid. So you have a threshold, a distance, inside which water is in gas form, outside which water is in form of snowflakes. So you have this snow line that you can cross. It's exactly like in the mountains, where you have snow on top and rain at the bottom. You have this boundary, which means that when you are going to build solids, planetesimals, aggregates, cores, with the solid material that is here, well, if you are inside the ice line, you do not have water, and you are going to make only rocky things and metal-rich things. If you are outside the ice line, you are going to produce bodies that contain a lot of H2O, and that would be typically something like a comet, a dirty snowball. That's a comet. Very dirty, by the way. Comets have about half water and half dirt. And also, it's important to remember, I will get back to this a bit later, that beyond the ice line, there's more solid and they are more sticky. Ice sticks very well, while sand does not quite stick, right? Otherwise, sand beaches would not be beaches, they would be rock. So you can make bigger embryos beyond the ice line. But I spoke here of H2O, but it's also true for all the other chemical species. You have an ice line for CO, an ice line for CO2, an ice line for CH4. Name a molecule, it has an ice line. So it means that the composition of the solids and of the gas depend on where you are in the protoplanetary disk, because a chemical species is either in the solids or in the gas. And the temperature depends on the distance, but it also depends slightly on the vertical distribution, a bit, marginally, and also it depends on time. As the disks spread and get slowly to a lower density, a lower opacity, they can cool. And if they cool, it means that at a given place, the temperature changes. And so what happens? The key question is whether the gas drifts faster or the temperature distribution drifts faster. It's illustrated by the sketch below. It's hard to read, I'm sorry, but this represents a gas disk. The star would be on the left, and here is the condensation line. Okay? So on the left, in pink, you have gas that is wet, full of H2O because it's hot. And on the right, you have dry gas where all the H2O has condensed in these dots, which are the solids. Now, as the gas drifts, because it's accreting onto the star, you have dry gas coming in while the wet gas is absorbed by the star. If the condensation line, where the temperature drops below the solidification line of water, is drifting slower, and is staying behind the gas, what you have is dry gas entering the inner region, and so there is never going to be condensation of the wet gas. Even though this region here is now too cold for water to be in vapor form, there is no more water vapor to condense, because the gas has come from the outer regions. In that case, the region inside the condensation line at time 0 will never get water. Never ever. Okay? Because water is in vapor form, the gas is gone into the star, and later on, after that, after you got rid of the water vapor because you got gas from the outer regions, which is dry, only after that the temperature drops and there's no more water to condense. And so you are left with the water only in the solids outside of the initial condensation line. Alright? Now this can be more tricky and more complicated if the solids containing water also drift inwards. If these guys drift faster than the condensation line, when they reach the condensation line, they evaporate. And they produce an evaporation front here where you have wet gas again. Maybe even wetter than before because there's a lot of these solids coming in. And in that case, as the condensation line is moving inwards, behind it there are always these icy solids that are drifting and following, and in front of it you have this evaporation front. So you see, the freezing of the situation is not so clear. Generally, this would happen where the solids keep moving, but we have seen also that disks have rings. There are many things that can block the solids, and so you can very well be in this situation. It all depends on the drift rate of the solids and how free they are to drift. And we will see this very soon, how the solids behave. Let us start with how the solids do behave, vertically speaking. I told you about sedimentation, that was the second step. The solids move with respect to the gas, which means they feel a drag, a friction force that is in a direction opposite to the relative velocity between the dust and the gas. Okay? So if you have a dust particle having an inclined orbit, from the point of view of the gas, which is not having inclined orbit, the gas is pressure supported, the particle is just moving up and down, up and down, up and down, and all the time it does it, it feels friction. You can do it, I can feel it with my hand, friction. So the motion is going to be damped. And this vertical motion, being damped, ends up in the midplane. Instead of having an inclined orbit and a cloudy distribution of the dust, like the zodiacal light, it all falls into the midplane. The typical time for this to happen is given by the stopping time here, which gives you, if you like, the stopping time quantifies how much friction there is between the dust parcel and the gas. It depends on the size of the dust aggregate. And if you are in a regime where the stopping time is very small compared to the orbital period, so omega Ts is very small with respect to 1, then the dust is very well coupled to the gas. It means it takes less than one orbit to stop the motion of dust with respect to the gas. And that would be the case for very small dust. It's typical of if you have very thin powder and you spread it in the air, you can see it moves, it follows the wind, and it does not fall down immediately. It takes a lot of time. It's typical when you have a blackboard and chalk. The powder of chalk is doing clouds, but eventually you will find it on the ground. But it takes a lot of time. It's very well coupled to the gas. In the case where the stopping time is super long compared to the orbital period, it means that it's going to take a lot of orbital periods for the friction to play a role, and so the dust is actually almost not filling the gas. The motion is almost Keplerian. That would be the case for the chalk piece with which you write. If you drop it, it just falls. It hardly feels the friction from the gas. And the most interesting regime is the one slightly in the middle, where the dust starts decoupling, wants to play on a Keplerian orbit, but the friction force is super strong and it damps it very efficiently. It's typical of the damped oscillator equation. You have the damped oscillations or the slow exponential convergence and the critical regime where the damping is fastest. So if we have an inclined orbit, the damping will be at some point efficient enough to converge towards the midplane. That's sedimentation. And I also know that if we have an eccentric orbit for a solid, it will have a radial motion with respect to the gas, and this will also be damped by the gas friction, and this will also lead to circularization of the orbit of the dust particle. So all the dust is going to have circular coplanar orbits. And it wants to follow a circular coplanar orbit with a Keplerian velocity. For dust, there's no pressure. But the gas is slightly sub-Keplerian, you remember? So the dust wants to go faster than the gas around the star, which means the dust is feeling a headwind from the gas, constantly. It's like if you're biking against the wind. You lose energy. If you lose energy, you eventually fall if you ride too much. But for dust, it loses orbital energy, so it moves closer to the star, deeper in the potential well of the star. It's losing angular momentum, and it will be drifting by making spirals converging towards the star because it's losing energy to the gas. Of course, the maximum efficiency for that is again this critical regime where omega Ts is of the order of 1. That corresponds to size of dust of the order of a centimeter or a meter, depending on the gas density and temperature. So this is a classical picture where the pressure gradient is negative, eta is positive, and the gas is sub-Keplerian. That's the classical thing. What if, at some point, pressure increases with the distance to the star? Then the coefficient eta will become negative, and at this location where the pressure increases, the gas is going to be super Keplerian and rotate actually faster than Keplerian. So the gas is going to push the dust behind. Give angular momentum, give energy to the dust, and the dust will accelerate and spiral out. Which means a region in the distribution of the disk where the pressure is maximum in radius is a perfect dust trap. If you move away from it outside, you feel a headwind, you move back in. If you move away from it inside, you feel a backwind, you move back out. This is just the perfect way of making rings in a disk. And actually, this is the first image I showed you. It was the first image made by ALMA. And there has been many more disks observed with ALMA. And in many of them, we find rings. Almost all of them have structures like that. Such a ring is very clearly a region where the pressure is maximum in the disk. Now these rings where the dust is concentrated are a great place to form planets because you have all the dust from around that is gathered here. You now just have to make the planet with it. On the other hand, having a planet in a disk is a great way of making the pressure have a maximum outside of the orbit of the planet because the planet will tend to repel a little bit the gas, so it will make a pressure maximum around its orbit. So it's a chicken and egg issue here. Do we have rings because we have planets, or do we have planets because we have rings? Or both, and reciprocally. There are ways of making density variations that can lead to pressure maxima. You can have rings without planets thanks to some magnetic properties inside the disk. Snow lines also change the pressure suddenly because you have some evaporation, an evaporation front at this location. So it's still an open question. Most likely, some rings are due to planets, some are not. Are all these rings permanent features that last for the whole life of the disk, or are they temporary and only last for a few thousand years before they get dissipated by some reason? We still don't know. There's a lot of research going on here, but it's clear that there are structures in the disk that are able to gather the dust, and that's cool. Now, About sedimentation, after sedimentation, we have aggregation. It's like at home where you do not clean your flat for a long time. Dust does not stay in the air. You know there's dust going on the ground, on the floor, on the shelves, everywhere. Dust is a pain. And when dust has accumulated on the ground, what does it do? It aggregates. And it makes little dust bunnies, you know, that you find below the bed, always, or behind a furniture. And that's what happens when you have small particles of dust that meet with one another, they stick. That's just physics, and it happens in protoplanetary disks just as it happens at home. And this is just a sketch, but here is now the result of a simulation by Guillaume Leb, where you see the dust distribution initially following the Gaussian vertical distribution of the gas with very small sizes. The blue color corresponds to the density of dust. And after 100,000 years here, all the dust has now decoupled from the Gaussian distribution of the gas and is now all in the midplane of the disk. And what you see on the bottom plot is the size of the dust. It started with micron-sized dust, and because they stick, eventually you get bodies of the size of a few centimeters. So just like that. How does dust grow and keep growing? When grains collide, they stick if they are small enough. That works up to about a centimeter. And then at some point, if they are too big, they may bounce, or they may even fragment and erode. This is something you can see at home when you don't clean for a long while. You never have meter-sized dust bunnies below your bed or behind a curtain. Never. Planet formation at some point stops, even at home. Because you see this as soon as you approach them with a vacuum cleaner or you want to wipe them, the biggest one, they fragment. They are super fragile. The bond between all these dust particles that is making the aggregate is not strong. So at small size, it's okay, but as soon as you have a larger size, you have a bigger lever arm to break them, and they are not solid enough to resist. Believe me, I've tried many times to make planet formation at home because it's my job. Never cleaned the apartment, never got a planet. This sketch is coming from a paper by Winmark et al., where they show the outcome of a collision between two grains, one with different sizes. The sizes are the x and y axes. And you see that as soon as you reach, if we follow the diagonal line, it will be a collision between two grains of the same size. As soon as they are bigger than a centimeter, the outcome is fragmentation. And if you have a big grain, bigger than a meter, meeting with another smaller grain, it will be erosion. So the growth is going to stop at some point. Green means you have sticking, or sticking with a bit of bouncing, or mass transfer. It's a positive growth, and red means nothing. You lose mass. So how to grow beyond the centimeter? A solution that they proposed in this paper was to win the lottery. That is, you are growing as a grain in size, moving to the right, but you always meet grains that are smaller than a millimeter. And these grains are going to stick, and you can grow this way all the way up to a kilometer. But you have really to win the lottery. It means that you have millions of collisions with grains that are smaller than a millimeter. If you ever meet a grain that is your size, you fragment. Now there are billions of grains in the disk, so one of them may win the lottery. Why not? But what we see mainly in this diagram is that there is a centimeter barrier where beyond the centimeter, it's in principle hard to grow. Also, the centimeter size corresponds to the one where the drift is most efficient. You remember the headwind with the gas? That's most efficient where omega Ts is of the order of 1. That is between the centimeter and the meter. So we have a double centimeter barrier, which is caused by the drift and the bounce and fragmentation. And I'm going to show you here a movie by Jean-François Gonzalez, who does in Lyon research on this topic. So you see, we started with small dust, very low in the y-axis, and it grows, that's the aggregation, up to a given size where it stops growing because it reaches the bouncing barrier and the fragmentation barrier. And what you can also see is that it moves in. It drifts. It's hard to perceive it, but it is really drifting inwards. And it starts drifting inwards at a size that depends slightly on the distance, but that always corresponds to this omega TS of the order of 1. So further away, it corresponds to smaller size. Closer in, it corresponds to a larger size. But the dust will grow and then drift. And you have this barrier. And you never make a planet like that, which is kind of a problem. What we see here is a protoplanetary disk, but not edge-on this time. We are here at a given radius around the star, and we see the cylinder corresponding to that. So imagine you are the star and you're having a panoramic view at what's going on exactly at a given radius. So you will see a dust thickness, and you are going to see the dust sediment and increase its density in the midplane, and then you are going to see interesting things. So you see the concentration of dust is increasing. It corresponds to a reddish or a yellow color. And we are following the Keplerian speed here. So you could see it was slightly sub-Keplerian, moving back. But now, because of the concentration of dust in the midplane, the dust wants to impose the Keplerian speed and to stay fixed in this frame. But the gas is still sub-Keplerian and pushing this way. And it generates turbulence in this layer where you have the dust staying at the Keplerian speed. The gas wanted to be sub-Keplerian. And as a result, this turbulence makes some vortices and concentrates dust. And the more dust is concentrated, the stronger it is to resist the gas drag. And so it will catch up all the dust that was alone. And this concentration is increasing and is growing and is eventually getting all the dust in one clump. It's like a bike race where you have a few guys that have escaped and gone first in front. After 100 kilometers, they get tired of having the headwind for themselves and they get caught by the mass of the crowd. So this is a way of concentrating dust into concentrating a lot of dust in a small region, which can eventually make bodies that would be of size maybe a kilometer, maybe even more. In one of the simulations by Anders Johansen, he even got objects of the size of Ceres. Of course, he had chosen very particular conditions, maybe not realistic, but very favorable for this mechanism. But you could go this way from centimeter aggregates to hundreds of kilometers, and you jump across the meter barrier. There are other processes that are roughly similar, all based on gas and dust interactions, typically the streaming instability and so on, that allow you to jump across this barrier. So we end up with planetesimals, objects bigger than 100 meters, which are now held together by gravity. The dust aggregates are held by van der Waals forces when the dust grains touch themselves. Now this is gravity giving these bodies their shape. For instance, the asteroid Itokawa is just a pile of rubble, a lot of rocks that are not connected to one another, but they are held together by the gravity. And this one, I think you could just give it a pinch and it would fly off, but it's still here because of the gravity of the object. And the asteroid Itokawa is a good example of an object made solely of rock and metal. No water here, almost no H2O. It was clearly formed out of solids that were inside the snowline. The nucleus of comet Wild 2, but we also have pictures of 67P, of course, are made of about half ice and half other stuff. And they were formed probably in this way by solids that were outside of the ice line. And now the question is, how can we grow even further than planetesimals? And it has been proposed by Lambrecht and Johansen 10 years ago, a mechanism that is extremely efficient called pebble accretion. Pebble is coming from solids with omega Ts of the order of 1. So the ones that I like because they start decoupling from the gas, but they are still feeling friction a lot. If you have such a body approaching a planetesimal, its trajectory is bent by the gravity of the planetesimal. And on this animation, you have the comparison between what's happening for a pebble feeling a strong gas friction and just a planetesimal that is a solid body that has omega Ts huge and does hardly feel the gas actually. If you do not feel the gas, you have a hyperbolic trajectory, typical of first year mechanics, right? You have all the conics due to the gravity potential, and the planetesimal is going to fly off, being deflected by the central object. But the red pebble is feeling gas friction, so when it starts having a bent trajectory, it has a lot of headwind because it's not following the motion of the gas. And so it's losing a lot of energy, and eventually it spirals onto the central object. So once you have some gravity that is able to modify the trajectories of the other solids, then you can accrete pebbles very efficiently. That's the key of pebble accretion. And so you are a big guy bending the trajectory of all the pebbles around and accumulating them. Pebble accretion is super efficient. It has a much larger cross-section than the pure gravitational focusing, as illustrated on the animation, and it leads to a runaway growth of the bodies because the more they accrete pebbles, the more efficient pebble accretion is, because the more they are able to deflect the trajectory of the pebbles. And so it's a way to grow from a small planetesimal to something of several Earth masses. And the key feature of that is that it's more efficient beyond the ice line, so you would form big cores, and it's less efficient inside the ice line, and that's called the great dichotomy of the solar system. It was published by these guys. Outside of the snow line, you have a lot of large pebbles because the ice is sticky, as I said earlier, so it's easy to grow up to the size that corresponds to omega Ts equal 1. And so you will have a super efficient pebble accretion, making 10 to 20 Earth mass solid cores. But inside the snow line, the solids are less sticky, so they have a hard time growing, and you remain at omega Ts of the order of 0.001 or 0.01, and pebble accretion is less efficient, and within the million years of lifetime of the disk, all you can form are what we call oligarchs, that are spherical objects of about 100th or a 10th of the mass of the Earth. So the mass of Mars or the mass of the Moon. So you see a clear dichotomy here in the solar system, whether or not pebble accretion is efficient. And then, if a protoplanet is big enough to create a pressure maximum outside of its orbit, and in the next session I will tell you about gap opening and how this works, at some point the planet is making a pressure maximum where the pebbles stop. So the planet is cutting itself from the flux of pebbles. The pebbles cannot reach the planet anymore, and so we call this the pebble isolation mass, where a planet grows by all the drifting pebbles that approach it, that it is able to absorb. But at some point, the planet is so big that it's blocking the pebbles, because it's making a pressure maximum in the gas. And this stops the growth of the planet, but it also stops the pebbles from drifting from outside in. You remember I told you that it's a key for the composition of the system, whether the pebbles can drift all the way to the star or they are stopped at some point. Well, a planet that has grown to 20 Earth masses can be a barrier. And then it separates two reservoirs of solids. The ones that are outside its orbit and the ones that are inside its orbit can never mix anymore. And it has been argued by Kreuger et al. In 2017 that Jupiter reached the pebble isolation mass at 1 million years in the solar system history, which is based on the fact that carbonaceous chondrites and non-carbonaceous chondrites have a different isotopic composition, in particular regarding elements that formed in the R process and the S process in supernovae, I'm not a master of that, but they noticed that there are clearly two reservoirs. And the only explanation they could find for that is that at some point in the formation of the solar system, there was a supernova in the cluster that has ejected a lot of elements that have enriched the solar system in these elements that are only produced in supernova. But this is seen only in the carbonaceous chondrites. So they must have been in the outer disk, fed with this wind from the supernova. And these elements have not reached the inner solar system, which has a very small cross-section and would have not been polluted a lot. So there must have been a barrier, and this barrier would have been Jupiter. Once we have reached the pebble isolation mass, we do not accrete solids anymore. So the way a planet grows is efficient solid accretion up to about 10 Earth masses, and then the mass of solids almost stay constant. But if you have reached a mass larger than 10 Earth masses, you are massive enough to be able to concentrate some gas of the disk. The gas of the protoplanetary disk is mainly hydrogen and helium, so it's light gas. So the Earth would not be able to keep it. The Earth is able to keep heavy gases like dioxygen and N2, but not H alone. But if you are massive enough, you can have some gas falling and concentrating around the planet. So this gas is compressed, so it heats, it becomes hotter. If it's hotter, it emits some radiation, and it cools down. And if it cools down, it concentrates more. And it leaves more room for more gas to come, which is compressed, heats, cools down, etc., etc. And you have a slow process where gas accumulates around this core, cools down, and accumulates, and cools down, and accumulates. And meanwhile, the planet becomes more and more massive, so it's more and more able to accumulate gas, and it heats, and it cools down, etc. So you have a slow phase where the gas is slowly accumulating onto the planet. So that's the dotted line is just the mass of gas, and the dashed dot line is the total mass of the planet. And at some point, generally, so after phase 1 and phase 2, when the gas envelope has about the same mass as the solid core, the gas envelope becomes unstable, collapses, and the process runs away, where you have now the planet is just compressing gas very efficiently, leaving room for more gas to come, etc., etc. And the planet grows to, as you see in this model, 100 Earth masses in a very short time. This is a typical sketch from now 25 years ago. Things have slightly evolved now. We do not see a clear divide between phase 2 and phase 3, but it's more a general exponential growth where, of course, you start slow and you then go on faster, but the general idea is the same. At first, gas growth is slow, and then gas accretion becomes fast. And so in this model, well, when you start from the massive body that is surrounded by a spherical envelope of gas and cools down, when you are in phase 2, you look pretty much like that. These two guys have masses of 17 and 14 Earth masses with a solid core which contains a lot of ices, which is about half their mass, or even more. So actually they are called ice giants rather than gas giants because most of their content is ices inside their core. Their core is more than half their mass. The atmosphere, the gas atmosphere of Uranus and Neptune is only 5 Earth masses-ish, and so the core is the rest, half of it being ices. So they are ice giants. But if you keep going all the way to the runaway accretion of gas, you get gas giants of 300 or 100 Earth masses, and that becomes a gas giant. So you have naturally a division between the giant planets in two classes, ice giants, gas giants, whether or not you reach this acceleration of the gas accretion. It's super hard to stop in between, right? If you have to be something, you will have to stop exactly here. Thin timing, hard to do. And what Michiel Lambrecht and his team have shown is that the isolation from the pebbles is what may trigger the runaway gas accretion, because as soon as you do not accrete solids by pebbles, you do not have the energy of the infalling solids to dissipate, so cooling is easier. And so you can start accreting gas more easily. And the time it takes to reach this pebble isolation mass is shorter in the inner solar system than in the outer solar system. And so they have this estimate of the trajectories of the planets at 5 AU, 10 AU, 20 AU, 30 AU. And you see that you do start accreting gas, so the fraction of solids drops faster at 5 or 10 AU than at 20 or 30 AU. And so it's easy to reach becoming a gas giant inside 10 AU, Jupiter and Saturn, and further away it takes more time, so you will never reach this phase and you become Uranus or Neptune. It makes a lot of sense. Now I will finish with the terrestrial planets. Inside 4 astronomical units, as I said earlier, pebble accretion is not efficient, and we think that we only formed solids that were 10 or 100 times less massive than the Earth. So you have to imagine that all the solids that correspond now to the terrestrial planets, so this represents something like 2 Earth masses, a bit more, were in the form of a lot of these embryos and planetesimals. And then the gas goes away. And this is clearly not a stable situation where you have all these bodies super close to one another in a narrow region, orbiting in close orbits. They will perturb each other's orbit, they will become eccentric, and they will collide, and they will merge, and they will eventually form 4 planets. And that's another movie that I need to show you. So we start with objects of at different distances from the Sun. These are small objects. The distance from the Sun is the x-axis. The y-axis is the eccentricity of these objects. So they all start on circular orbits, because I told you the gas tends to circularize everything. And the color corresponds to the content of water inside these bodies. Red, they are only super dry. Blue, they are half ice. And we start the simulation, which is just n-body simulation. So they just orbit around the Sun and feel each other's gravity and perturb each other. As soon as you start this, there's no gas, no more circularization effect, the eccentricities grow. As the eccentricities grow, it means that their orbits cross and they merge. And you see less and less bodies who become bigger and bigger. And you can start seeing also that the bodies that were here are getting some yellowish, greenish color, which means they are accreting bodies that were coming from outside. So with all this mixing, now, finally, you have water delivered in the terrestrial planet region. It's not a lot of water, but it's enough to give us some water at least. And you see that the simulation reaches a stable state when you have only 3, 4, or 5 planets that are massive enough and have eaten all the planetesimals. And that's typical of all these simulations. So this is how terrestrial planets form. You have a swarm of planetesimals and embryos that becomes unstable, and eventually the system is stable only when they are just a few, having merged with one another. And this is bringing water to Earth, and that's all the water we have on Earth. This is a representation of the water content of the Earth, all the water at the surface of the oceans plus the water in the mantle. Water is only 0.04% of the composition of the Earth. The Earth is truly a dry planet. Of course, it's covered in 70% of the surface by water, but it's just a very thin layer. In volume, that's all the water we have. And all these impacts among bodies, well, the last of them on the Earth would be an impact by a planet, a body that had almost the size of Mars, so a tenth of the mass of the Earth, that is often called Theia. This impact would have been grazing, almost horizontally arriving here at the top of the Earth, and it ejects a lot of material in orbit around the Earth, which eventually falls down. But not only, it forms a disk of silicates you can imagine a disk of molten lava around the Earth after this impact, and this disk of molten lava is going to spread inwards, fall onto the Earth, and outwards accumulate and form the Moon. The reason why the Earth has a moon, which is quite a massive satellite, about 1% its mass, is because of this last impact that had been grazing. If it had not been grazing, we would not have a moon. But it was, and so we do have a moon. And I did not mention, but this will be my last slide for this part, the formation of the satellites around other planets. You know that giant planet satellites could very well be habitable. They are almost among the most promising places to look for extraterrestrial life in the solar system. We know that there is volcanism on Io, on Jupiter. We know that Europa has a liquid water ocean below the ice shelf on the crust. And we know that there are geysers on Enceladus, which is a satellite of Saturn. So satellites of giant planets are super interesting places. And when a giant planet forms, well, classically it accretes gas, as I told you, and at some point it's so massive that the gas falling onto the planet will also form a disk. And so you have a circumplanetary disk, not a protoplanetary disk, but a circumplanetary disk, so a disk around the planet. And inside this disk of gas and dust, you can take all these slides and repeat the process, and you should have some planetary formation around a planet. So this is going to form the satellites. Of course, there are differences because the gas and the dust will not have the same ratio. It's not clear whether the dust can cross, etc. It's super complex. But basically, the idea is a giant planet surrounds itself with a disk of gas and dust. Inside this disk, well, you had growth of solids, and you eventually form spherical bodies that are in orbit around the central one. That's the satellites of the giant planets, and it's typically what explains the Galilean moons of Jupiter. It works very well. There is another way of forming satellites, which is what probably happened around Saturn. It's that the rings of solids, like Saturn's rings, also spread. And when they crossed the Roche limit, which is at about 2.5 radius of the planet, and it's the distance beyond which the self-gravity of these solids is going to dominate against the shear of the Keplerian orbit that wants to separate them, which is also corresponding to the tidal forces of the planet. Across the Roche radius, the solids are going to accumulate, and they form moonlets, which are orbiting slower than the rings, so they are given angular momentum by the rings by the gravitational interaction, and they drift away. And as these satellites move away, they eventually merge and grow. And as the rings spread, you form a series of satellites like that, which have a mass distance distribution, where the mass is about the square of the distance to the rings. That's what comes out of calculations of this process, analytical calculation, and it fits very nicely the mass distance relationship that is observed in Saturn's satellites. So probably this is the way Saturn's satellite formed, including Enceladus. And the same mass distance relation is observed around Uranus and Neptune. So we think that this is a generic process that happened also around Uranus and Neptune, but then Uranus and Neptune have lost their rings. And in the end, the physics of this is the same as the physics of a fast spreading magma disk around the Earth to form one single moon. If the spreading is fast, you have only one satellite that is accumulating all the material. If the spreading is slow, then the satellites form little by little, and you have a series of satellites like around the giant planets. Okay? That's my conclusion for now, before the break, that planets form in protoplanetary disks of gas and dust around young stars. It takes a few million years. It happens in a plane containing the star. And you have more or less mixing and drift of dust bunnies in the process. And naturally, you form giant planets far from the star, beyond the ice line, and small, dry terrestrial planets close to the star. Then the disk dissipates, you finish the formation of the terrestrial planets forming the moon, and you have a planetary system that stays the same for billions of years, and then you should have the same thing happening around all the stars, which is cool, and you wonder why there is a second part to this lecture. But you will see that after the break.